On a clear night, far from city lights, you can see it stretching across the darkness above you. A faint, cloudy band of light, like a river flowing through the stars. The ancient Greeks called it Galaxias Kyklos, the Milky Circle. The Romans knew it as Via Lactea, the road of milk. To the Norse, it was the path of ghosts traveling to the afterlife. Cultures across the world have looked up at this luminous ribbon and woven it into their stories, their myths, their understanding of the cosmos. But here's the beautiful paradox. When you look at the Milky Way, you're not looking at something distant. You're looking at home. You're inside it, seeing it from within, like standing in a vast city and trying to understand its shape by looking at the buildings around you. Every star you can see with your naked eye, every constellation you've learned to name, every point of light that's caught your attention on a dark night, they're all part of this galaxy. They're all neighbors, cosmically speaking, residents of the same enormous spiral of stars and gas and dust that we call home. For most of human history, we didn't know this. We saw the band of light, but we couldn't understand what it meant. We didn't know we were living inside a disk of hundreds of billions of stars spinning slowly through space. We didn't know that the Sun was just one star among countless others, orbiting a distant center we couldn't see. We certainly didn't know that this galaxy was just one of trillions scattered throughout a universe so vast it challenges comprehension. The first glimpse of truth came in 1610, when Galileo Galilei pointed his telescope at that milky band and discovered something remarkable. The cloudy glow resolved into stars, thousands upon thousands of individual points of light, so numerous and so distant that they blended together for the naked eye. The Milky Way, he realized, was made of stars, but even Galileo couldn't grasp the full picture. He couldn't know that he was looking at our own galaxy from the inside, seeing the combined light of billions of suns too far away to distinguish individually. It would take another 3 centuries before we truly began to understand where we are. In the early 20th century, astronomers gradually pieced together the architecture of our cosmic home. They realized that we live in a flattened disk of stars, not at the center, but far out toward the edge. They discovered that the Milky Way is a spiral galaxy with great arms of stars and gas curving through space. They found that we're just one galaxy among countless others, part of a universe far larger and far more spectacular than anyone had imagined. And yet even today, mapping the Milky Way remains one of astronomy's greatest challenges. We're embedded in it, surrounded by dust that obscures our view, trying to understand the shape of something we can only see from the inside. It's like being a single cell in your body, trying to figure out what the whole organism looks like. You can observe your immediate surroundings. You can make measurements, gather data, build models. But you'll never have that perfect, complete view that comes from seeing the whole picture at once. So what does our galaxy look like from the outside? If you could somehow travel beyond it, far out into the darkness of intergalactic space, and turn around to look back, what would you see? And what does our home compare to others across the cosmos? These are the questions we'll explore together as we drift through understanding, piecing together the portrait of our galactic home, the Milky Way. The architecture of spirals. Imagine you could step outside the galaxy, traveling hundreds of thousands of light years out into the void until the Milky Way lay before you like a vast cosmic mandala. What you'd see would be breathtaking in its elegance and complexity. A flattened disk of stars, glowing with the light of hundreds of billions of suns, stretching roughly 100,000 light-years from edge to edge, or more precisely, about 87,000 light-years by the most recent measurements, but remarkably, wonderfully thin, only about 1,000 light-years thick at the spiral arms, like a dinner plate compared to its diameter. At the center you'd see a bright bulge, egg-shaped and glowing with the combined light of ancient stars packed closely together. From this bulge, a bar extends outward, a thick structure of stars that forms the backbone of the galaxy. And from the ends of this bar, great spiral arms sweep outward and around, curving through the disk like cosmic pinwheels frozen in a slow dance. But here's what's fascinating about these spiral arms. They're not solid structures. They're not fixed groups of stars that always stay together as they orbit the galactic center. Instead, they're something far more interesting. They're density waves like traffic jams in space. Think of it this way. Imagine cars on a circular highway. Each car travels at its own speed depending on how far it is from the center. Cars on the inner lanes move faster, completing their circuits more quickly. Cars on the outer lanes move slower, taking longer to go around. Now imagine that occasionally cars bunch up, creating areas of higher density where traffic slows down. These bunched-up regions rotate around the highway at their own speed, different from the speed of individual cars. A car might enter a traffic jam, slow down temporarily as it passes through the congested area, then speed up again as it emerges on the other side. The traffic jam itself persists, rotating around the highway even though it's constantly made up of different cars. This is essentially what's happening in the spiral arms of the Milky Way. The arms are regions of higher density, areas where stars and gas clouds are more concentrated. As stars orbit the galactic center, they pass through these density waves, spending some time in the spiral arms before emerging into the less dense regions between them. The arms themselves rotate around the galaxy, but at a different speed than the stars that make them up. The pattern persists, even as the contents change. This is why spiral arms are such active places. When gas clouds enter these density waves, they get compressed, and compressed gas clouds are exactly the conditions needed to trigger the birth of new stars. So the spiral arms light up with brilliant blue young stars, massive and hot and short-lived, born from the compressed gas. These stars don't last long enough to drift far from where they formed, so they remain in the spiral arms, making the arms appear bright and well-defined. Meanwhile, older, longer-lived stars like our Sun have had time to wander away from their birthplaces, filling the regions between the arms. The Milky Way's spiral structure emerges from a central bar, a thick, elongated structure of stars that forms the galaxy's skeleton. This bar wasn't always part of our understanding of the Milky Way. In fact, astronomers only began to suspect its existence in the 1960s, and it wasn't confirmed until the Spitzer Space Telescope made infrared observations in 2005. The reason it took so long to discover is that we're inside the galaxy, looking at the bar almost end-on, which makes it incredibly difficult to recognize. The bar is substantial. It extends from the very center of the galaxy out to about 5,000 parsecs, roughly 16,000 light-years. At its heart, It has a peanut-shaped structure, a three-dimensional bulge that we observe as a boxy bulge when we look toward the galactic center. This central bar contains somewhere between 30 and 40% of all the stellar mass in the entire galaxy. It's not a minor feature. It's fundamental to the galaxy's architecture. The bar rotates like everything else in the galaxy, but at its own characteristic speed. It completes one full rotation roughly every 160 to 180 million years. This rotation helps maintain the spiral structure, funneling gas inward and outward, helping to regulate where stars form and how the galaxy evolves over time. From the ends of this bar, the major spiral arms emerge. Based on recent observations, astronomers have identified 4 main spiral arms in the Milky Way. The 2 major ones are the Scutum-Centaurus arm and the Perseus arm. These contain the highest densities of both young and old stars. Then there are 2 more minor arms, the Sagittarius arm and the Norma arm, sometimes called the outer arm. These are less prominent, filled more with gas and pockets of star-forming activity than with the continuous streams of stars that characterize the major arms. The spiral pattern isn't perfectly uniform. There are segments and spurs, breaks and reconnections. Some regions show clear spiral features, while others are more fragmented. The local arm, where we live, might be an independent arm segment or a spur connecting larger arms. Astronomers are still working out the details. The structure is complex, messy in the way that real things often are, more intricate than any simple model could capture. Mapping all of this has been an extraordinary challenge. When you're inside a galaxy, you face several problems. First, there's dust, interstellar dust, made of tiny particles of carbon, silicon, and other elements, fills the disk of the galaxy. This dust absorbs visible light, particularly light from the blue end of the spectrum, making distant stars appear dimmer and redder than they actually are. Dust clouds can completely obscure entire regions, creating dark patches where we simply can't see anything in visible light. For decades, this dust made it nearly impossible to map the galaxy's structure. Astronomers could see nearby stars clearly, but more distant regions remained hidden. They could detect radio waves, which pass through dust unhindered, revealing the distribution of cold hydrogen gas. But connecting these observations into a coherent picture of spiral arms proved difficult. The breakthrough came with infrared observations. Infrared light, with its longer wavelengths, can penetrate dust much more effectively than visible light. Space telescopes like Spitzer, looking in infrared wavelengths, could finally see through the dusty veil and observe stars throughout the galaxy. These observations revealed the bar structure clearly for the first time and helped trace the spiral arms with much greater accuracy. More recently, the Gaia Space Telescope has been revolutionizing our understanding by making incredibly precise measurements of the positions and motions of more than 1 billion stars. By tracking how stars move, astronomers can identify patterns that reveal the presence of spiral arms and the bar. Stars near spiral arms show characteristic motions, systematically moving inward toward the arm as they approach it, consistent with density wave theory. This enormous data set is still being analyzed, and each new data release from Gaia refines our picture of the galactic structure. Even with all these tools, uncertainties remain. The exact pitch angle of the spiral arms, the precise boundaries between different structural features, the detailed three-dimensional shape, these are still subjects of active research. Papers published in recent years give different numbers for how many distinct spiral features exist, how they connect, and what they should be called. This isn't a failure of science. It's a testament to the genuine difficulty of mapping something so vast and complex from our embedded position within it. But the picture that's emerging is spectacular. A barred spiral galaxy, mature and grand, with a strong central bar, clear spiral arms, a bright central bulge, and a flattened disk extending outward into space. A structure shaped by gravity and rotation, by density waves and star formation, by billions of years of slow evolution. A galaxy not unlike billions of others scattered throughout the universe, and yet, to us, utterly unique. Because it's ours. Because we're part of it. Because every star we'll ever see with our eyes or our telescopes belongs to this elegant spiral structure, this island of stars we call the Milky Way. Our cosmic address. If the Milky Way is our home, then it's worth knowing exactly where in this vast structure we live. Our address, cosmically speaking, is both precise and wonderfully poetic. The solar system, the Sun and all its planets, including Earth, resides in what's called the Orion Arm, sometimes known as the Orion Spur or the Local Arm. This region of the galaxy gets its name from the constellation Orion, because when we look in that direction, we're looking into our own spiral arm. Many of the brightest and most familiar stars in our night sky, Betelgeuse, Rigel, the three stars of Orion's belt, the Orion Nebula, are all part of this same galactic structure where we reside. For a long time, astronomers thought the Orion Arm was a minor structure, just a small spur connecting the more prominent Perseus Arm and Sagittarius Arm, which lie on either side of us. But recent observations have revised this understanding. The Orion Arm turns out to be more substantial than previously believed. It stretches for approximately 20,000 light-years through the galaxy and measures roughly 3,500 light-years wide. While still not as prominent as the two major spiral arms, it's significant enough that some researchers now argue it should be considered a proper arm in its own right, making it the fifth major feature in the Milky Way's spiral structure. Within this arm, we sit close to the inner edge, about halfway along its length. More specifically, the Sun lies approximately 27,000 light-years from the galactic center, roughly halfway from the center to the visible edge of the galaxy. Some measurements suggest 26,000 light-years, others say 28,000. The uncertainty reflects the genuine difficulty of measuring these vast distances precisely. But the general picture is clear. We're in the galactic suburbs, not in the downtown area, and not quite out in the rural outskirts either. Our position also places us in what's called the local bubble, a region of space that's relatively empty of interstellar gas and dust. This bubble formed from supernova explosions in our cosmic neighborhood over the past several million years. These explosions swept up the surrounding material, creating a cavity of low-density, hot gas. The local bubble extends for several hundred light-years around us, giving us a relatively clear view of nearby stars compared to dustier regions of the galaxy. This location matters more than you might think. Being situated between the major spiral arms means we're in a relatively quiet region of the galaxy. We avoid the intense radiation and frequent supernova explosions that happen in the densest parts of the spiral arms, where massive stars are constantly being born and dying. At the same time, we're far enough from the galactic center to avoid the intense gravitational disruptions, the tidal forces, and the bursts of radiation that characterize the inner regions where stars are packed much more closely together. Some astronomers have suggested that there might be a galactic habitable zone, a region of the galaxy where conditions are most favorable for the development of life, too close to the center, and planets would face too much radiation, too many close stellar encounters, too much chaos, too far toward the outer edges, and there might not be enough heavy elements, the carbon, oxygen, nitrogen, and other elements besides hydrogen and helium that are necessary for rocky planets and organic chemistry. These elements are made in stars and dispersed by supernovae, so regions where star formation has been active but not too violent might offer the best conditions. The Orion Arm, in the galactic suburbs, about halfway out, this seems to be a pretty good neighborhood. It's been stable for a long time. The Sun has been orbiting at roughly this distance from the galactic center for its entire 4.6 billion year life. And in all that time, it's managed to complete only about 20 to 25 full orbits around the galaxy. Let that sink in. 20 to 25 times around in 4.6 billion years. That's because a galactic year, the time it takes the Sun to orbit once around the center of the Milky Way, is about 225 to 230 million Earth years. Think about what that means. The last time the solar system was in approximately the same position relative to the galaxy that it is now, the age of dinosaurs was in full swing. Massive reptiles dominated the Earth, flowering plants hadn't yet evolved, and the continents were arranged differently than they are today. Go back another orbit before that, and you're looking at a time before dinosaurs even existed, when proto-mammals were just beginning to emerge. Human civilization, all of recorded history, every empire that has risen and fallen, every discovery and invention, all of it has happened in less than 1/100th of a single galactic year. We are so brief. And yet, despite this brevity, despite how recently we arrived on the scene and how insignificant we are in galactic terms, we've managed to figure out where we are. We've mapped our position. We know we're moving through space, carried along by the Sun's orbit around the galactic center at about 250 kilometers per second. That's around 558,000 miles per hour. Every second we travel 250 kilometers through space relative to the galactic center, and we don't feel it at all, any more than we feel the Earth spinning or orbiting the Sun. The solar system's motion isn't just circular, though. We also bob up and down, oscillating above and below the galactic plane like a cosmic sine wave. Right now, the Sun is positioned slightly above the mid-plane of the galactic disk, somewhere between 16 and 98 light-years above the central plane, depending on which measurement you consult. As we orbit, we cross through the plane approximately every 30 million years or so, moving from above to below and back again. When you look up at the night sky and see the Milky Way band, you're seeing the galaxy edge on from our position within the disk. Most of what you see lies in the galactic plane, the central thin region where most of the stars and dust are concentrated. The brightest part of the Milky Way, visible in the constellation Sagittarius, marks the direction toward the galactic center, though the center itself is hidden behind thick clouds of dust that block visible light. In the opposite direction, toward the constellation Auriga and Taurus, you're looking outward toward the edge of the galaxy. There's less to see in that direction because there's less galaxy beyond us, fewer stars, more emptiness stretching out into intergalactic space. Every star you can see with your unaided eye is part of our local neighborhood. They're almost all within a few thousand light-years of the Sun, fellow residents of the Orion Arm or neighboring regions. The most distant star you can see with the naked eye under perfect conditions is probably V762 Cassiopeia, roughly 16,000 light-years away. But that's exceptional, a rare, extremely luminous star. Most naked-eye stars are far closer, well within 1,000 light-years. The constellations you've learned, the patterns humans have traced in the stars since ancient times, Orion, the Big Dipper, Cassiopeia, the Southern Cross, all of these are local features. They're patterns we see only because of our specific position in this particular spiral arm of this particular galaxy at this particular moment in cosmic time. Travel a few thousand light-years in any direction, and the familiar patterns would disappear, replaced by entirely different arrangements of stars. This is our cosmic address then, the Milky Way galaxy, Orion Arm, about 27,000 light-years from the center, slightly north of the galactic plane, third planet from a yellow dwarf star, circling that star once per year, circling the galaxy once every 225 million years, embedded in a structure so vast it's difficult to fully comprehend, and yet feeling utterly, intimately at home. Nurseries of light. All around us, throughout the spiral arms and the disk of the Milky Way, an ancient process continues. Stars are being born. Right now, at this very moment, in vast clouds of gas and dust scattered throughout the galaxy, gravity is gathering matter together, compressing it, heating it, until the conditions become right for nuclear fusion to ignite, and a new star begins to shine. The raw material for star formation fills the space between the stars. It's called the interstellar medium, a thin mixture of gas and dust that exists throughout the galaxy. Most of it is hydrogen, the simplest and most abundant element in the universe, along with helium and traces of heavier elements. In most places, this material is spread incredibly thin, just a few atoms per cubic centimeter. But in certain regions it collects into clouds. And within those clouds, the density increases dramatically. The densest, coldest clouds are called molecular clouds because the conditions are right for hydrogen atoms to pair up into H2 molecules. These molecular clouds are the stellar nurseries, the places where star formation happens. The Milky Way contains an estimated 6,000 such clouds, each one containing more than 100,000 times the mass of the Sun. Some are much larger. The largest molecular clouds can contain millions of solar masses of material sprawling across hundreds of light-years of space. Within these clouds, the temperature drops to just a few degrees above absolute zero. It's bitterly cold, far colder than interstellar space in general, because the dense dust shields the interior from starlight and the warmth it brings. The clouds are dark, opaque, visible only as black silhouettes against the background stars or by the infrared glow of dust warmed by embedded young stars. Star formation begins when a region within a molecular cloud reaches a critical density. This can happen through several mechanisms. Sometimes it's simply random fluctuations in the cloud's density, a region where the gas happens to be a bit denser than average. More often, something triggers the collapse. A shock wave from a nearby supernova can compress the gas. The collision of two molecular clouds, driven together by galactic rotation and turbulence, can create dense regions. Even the passage of the cloud through a spiral arm's density wave can provide the compression needed to tip the balance. Once a region becomes dense enough, gravity takes over. The material begins to collapse inward, pulled together by its own gravitational attraction. As it collapses, it heats up. Gravitational potential energy converts to thermal energy. The collapsing region fragments into smaller clumps, each one potentially becoming a star or a small group of stars. The collapse continues over hundreds of thousands of years, and the central clump grows hotter and denser. This is the protostar phase. The object is glowing now, warm from compression, but it's not yet a star. It doesn't have nuclear fusion happening in its core. It's still collapsing, still gathering material from the surrounding cloud, growing in mass and temperature. Finally, if the protostar gathers enough mass, the pressure and temperature at its core reach the critical threshold. Hydrogen nuclei begin to fuse together, forming helium and releasing energy in the process. Nuclear fusion ignites. The protostar becomes a star, entering the main sequence phase of its life, where it will remain stable for millions or billions of years, fusing hydrogen into helium and radiating energy into space. The Milky Way is remarkably efficient at producing stars, though not as efficient as you might think. Despite the enormous amount of gas available in molecular clouds, only about 1% of it actually ends up becoming stars. The rest is prevented from collapsing by turbulence in the gas, by magnetic fields threading through the clouds, and by feedback from the stars that do form. When massive stars are born, they're powerful and disruptive. They emit intense ultraviolet radiation that heats and ionizes the surrounding gas. They generate fierce stellar winds that blow material away. These processes can both trigger and inhibit star formation in the surrounding cloud. They can compress nearby gas, triggering new rounds of starbirth, but they also disperse the cloud, preventing further collapse. Eventually, the most massive stars will explode as supernovae, blasting the remaining cloud material into space and ending the star-forming episode. Recent studies using gamma-ray observations of aluminum-26, a radioactive isotope created in massive stars, and their supernova explosions, suggest that the Milky Way's star formation rate might be higher than previously estimated. Earlier calculations suggested about 2 solar masses of new stars per year. The newer measurements indicate it might be closer to 4 to 8 solar masses per year. That translates to roughly 10 to 20 individual stars being born annually, though most of these are low-mass stars much less massive than the Sun. That might not sound like much. 20 new stars per year in a galaxy of hundreds of billions. But over the 13.6 billion-year history of the Milky Way, that steady rate adds up. And it's enough to maintain a vibrant, active galaxy, constantly renewing its stellar population. We can see stellar nurseries scattered throughout the galactic disk. The most famous and the nearest major star-forming region is the Orion Nebula, located about 1,300 light-years away in the constellation Orion. On a clear, dark night, you can see it with your naked eye as a fuzzy patch in Orion's sword, hanging below the 3 stars of Orion's belt. Through a telescope, it reveals itself as a glowing cloud of gas, illuminated by hot young stars embedded within it. The Orion Nebula has been forming stars for about 3 million years and contains roughly 700 stars in various stages of development. Even closer is the Rho Ophiuchi cloud complex, only about 400 to 450 light-years away. This region is too heavily obscured by dust to see well in visible light, but infrared observations reveal it as an active stellar nursery with dozens of young stars and protostars. One of the most iconic star-forming regions is the Eagle Nebula, home to the famous Pillars of Creation. These towering columns of gas and dust, immortalized in a stunning Hubble Space Telescope image, are regions where star formation is actively occurring. The pillars are sculpted by the intense radiation from nearby young stars, which erodes the less dense material while leaving behind the denser cores. Within those dense cores, protected from the harsh radiation, protostars are forming. The Carina Nebula, about 7,500 light-years away, is another spectacular stellar nursery. It's one of the largest and brightest nebulae in the sky, though it's visible only from southern latitudes. The Carina Nebula hosts some of the most massive stars known, including Eta Carinae, a star so massive and unstable that it's expected to explode as a supernova sometime in the next few million years. When it does, it will briefly outshine the entire galaxy. These nebulae glow because of the stars forming within them. Young, massive stars emit copious ultraviolet radiation. This high-energy light strikes the surrounding hydrogen gas, stripping electrons from the atoms, ionizing them. When these electrons recombine with hydrogen nuclei, they emit light at specific wavelengths, particularly the red light of the H-alpha emission line. This gives many star-forming nebulae their characteristic pink or red color in photographs. The process isn't gentle. Star formation, particularly the formation of massive stars, is violent and dramatic. The young stars don't just illuminate their surroundings, they sculpt them. Stellar winds and radiation carve intricate structures in the gas, creating pillars, bubbles, and cavities. Over time, the most massive stars will explode as supernovae, sending shockwaves through the remaining cloud. These shockwaves can compress nearby gas, triggering a new generation of star formation, even as they destroy the cloud that gave birth to the original stars. This is why star formation often happens in waves along spiral arms. As a molecular cloud enters the density wave of a spiral arm, it gets compressed, triggering star formation. The most massive stars form quickly and die quickly, exploding as supernovae while still in the spiral arm. These explosions trigger more star formation, creating a cascade of stellar birth. By the time the cloud exits the spiral arm, much of its gas has been used up or dispersed, and star formation ceases. The stars that form aren't all the same. There's a distribution, with many more low-mass stars than high-mass ones. For every star as massive as 10 suns, there are thousands of stars similar to the Sun or smaller. The smallest stars, red dwarfs with masses only a tenth that of the Sun, are by far the most common. They burn their hydrogen fuel so slowly that they can shine for trillions of years. longer than the current age of the universe. These stars are divided into populations based on their chemical composition. Population I stars like our Sun are relatively rich in elements heavier than helium, what astronomers call metals, even though many of them, like carbon and oxygen, aren't actual metals in the chemical sense. These stars formed more recently from gas that had been enriched by previous generations of stars. Population II stars, in contrast, are metal poor, having formed early in the galaxy's history from more pristine material. They're found mainly in the galactic bulge, the halo, and in globular clusters, ancient stellar systems that orbit the galaxy like satellites. Every star you see, every point of light in the night sky, began in a stellar nursery somewhere in the galaxy. They condensed from clouds of gas, gravitationally collapsing, heating up, igniting fusion in their cores. The light from those stars has traveled across dozens or hundreds or thousands of light years to reach your eyes, carrying information about these distant suns, these scattered islands of warmth and light embedded in the cold darkness between the stars. And the process continues. Even now, even as you read these words, stars are being born in molecular clouds throughout the Milky Way. Gravity is gathering gas, protostars are heating, fusion is igniting. New points of light are appearing in the galactic night. The ancient cycle of stellar birth continues, as it has for billions of years, as it will for billions more, until the galaxy finally exhausts its supply of cold gas and the nurseries fall silent. But that time lies far in the future. For now, the Milky Way remains vibrant, alive, birthing new generations of stars. The end of starlight. Stars are born, they live, and eventually they die. But stellar death is not an ending in any simple sense. It's a transformation, a return of material to the cosmos, and often a spectacular release of energy that shapes the galaxy and enables new cycles of creation. Not all stars die the same way. Their ultimate fate depends primarily on their mass. Low-mass stars, those with masses similar to or less than the Sun, die relatively gently. They live long lives, billions or even trillions of years, burning their hydrogen fuel at a measured pace. Eventually, the hydrogen in their cores runs out. The core contracts and heats up, while the outer layers expand dramatically, turning the star into a red giant. For a star like the Sun, this phase will begin about 5 billion years from now. The Sun will swell to perhaps 100 times its current diameter, its outer layers reaching beyond the orbit of Mercury, possibly even beyond Venus. Earth, if it survives, will be scorched, its atmosphere and oceans boiled away into space, leaving a dead cinder. But this dramatic expansion is just a phase. The red giant stage is unstable, and eventually the star will shed its outer layers in a series of pulses, creating an expanding shell of glowing gas. A planetary nebula, though it has nothing to do with planets. The name comes from early telescopic observations that made these objects appear planet-like. What remains at the center is the star's core, now exposed, a hot, dense ember called a white dwarf. This remnant is incredibly compact, packing roughly the mass of the Sun into a sphere about the size of Earth. White dwarfs don't generate energy through fusion. They simply radiate away their residual heat over billions of years, gradually cooling and dimming until they become dark, cold spheres of ultra-dense matter. But for more massive stars, those with at least 8 to 10 times the mass of the Sun, the story ends far more dramatically. These stars burn through their fuel much faster, living only a few million years compared to the billions that smaller stars enjoy. They fuse hydrogen into helium, then fuse helium into carbon and oxygen, then continue up the periodic table, building heavier and heavier elements in their cores: neon, magnesium, silicon, and finally iron. Iron is the end point. Fusing iron doesn't release energy, it consumes energy. Once a massive star's core has been converted to iron, there's no more fuel left. The core can no longer generate the outward pressure needed to balance gravity. And so, suddenly and catastrophically, the core collapses. The collapse is almost unimaginably rapid. The core, roughly the size of Earth but containing more mass than the Sun, implodes in less than a second. The material reaches nuclear densities compressed to the point where protons and electrons merge to form neutrons. The collapse halts abruptly, and the rebounding shock wave, energized by intense floods of neutrinos, blasts the star's outer layers into space at speeds of tens of thousands of kilometers per second. This is a supernova. For a few weeks, a single exploding star can shine as brightly as an entire galaxy, outshining the billions of other stars combined. At its peak, a supernova can release more energy than the Sun will emit over its entire 10 billion-year lifetime. It's one of the most violent events in the universe, a cosmic explosion of staggering power. What remains depends on the mass of the original star. If the core is between about 1.4 and 3 solar masses, it becomes a neutron star, an object so dense that a sugar cube-sized piece of it would weigh as much as a mountain on Earth. Neutron stars are typically only about 20 kilometers across, yet they can spin hundreds of times per second, and they have magnetic fields trillions of times stronger than Earth's. Some neutron stars emit beams of radio waves from their magnetic poles. As they spin, these beams sweep across space like lighthouse beams. If one of these beams happens to point toward Earth, we detect it as a pulsar, a celestial object that appears to pulse with remarkable regularity. If the collapsing core is even more massive, typically above 3 solar masses, nothing can stop the collapse. The object becomes a black hole, a region of space-time where gravity is so strong that not even light can escape. The matter that made up the star's core crosses the event horizon and is lost from the observable universe, leaving behind only gravitational influence like the grin of the Cheshire Cat. The last supernova directly observed in the Milky Way with the naked eye was Kepler's supernova in 1604. It appeared suddenly in the constellation Ophiuchus, growing bright enough to be visible in daylight, then gradually fading over the following months. Before that, Tycho's supernova had appeared in 1572, also visible in daylight. These events had profound effects on European astronomy because they challenged the Aristotelian belief that the heavens were unchanging and eternal. Based on observations of supernova remnants and statistical studies of other galaxies, astronomers estimate that supernovae occur in the Milky Way roughly 3 times per century on average. But we haven't seen one in over 400 years. The reason is dust. Most of the galaxy is hidden from our view by interstellar dust, particularly the inner regions where stars are more numerous and supernovae more frequent. A supernova could explode in the inner part of the galaxy, and we might never see it in visible light. though we might detect it in radio waves or X-rays or neutrinos. The supernova remnant Cassiopeia A, located about 11,000 light-years away, is the remnant of a supernova that occurred around 1667. It was probably visible from Earth, though curiously, there are no confirmed historical records of its observation. The explosion left behind an expanding shell of gas racing outward at about 10 million miles per hour. In 1999, the Chandra X-ray Observatory found the neutron star at the center, the ultra-dense core left behind by the explosion. The Crab Nebula, another famous supernova remnant, resulted from an explosion observed by Chinese astronomers in 1054 CE. They recorded the appearance of a guest star in the constellation Taurus, bright enough to be visible in daylight for 23 days and visible at night for nearly 2 years. At the center of the expanding gas cloud lies a pulsar, spinning 30 times per second, the remnant core of the exploded star. Supernovae are not just spectacular events, they're essential to the chemical evolution of the galaxy and the universe. Remember that stars form from clouds of gas that are mostly hydrogen and helium, the primordial elements created in the Big Bang. But the universe today contains a rich array of heavier elements: carbon, oxygen, nitrogen, iron, gold, uranium. Where did these elements come from? They were created in stars. As stars fuse hydrogen into helium, helium into carbon, and so on, they build up heavier elements in their cores. But these elements remain trapped inside the star until it dies. When a low-mass star sheds its outer layers as a planetary nebula, it returns helium, carbon, and oxygen to the interstellar medium. When a massive star explodes as a supernova, it disperses everything it created: carbon, oxygen, silicon, iron, and all the other elements up to uranium and beyond. The explosion itself creates additional elements through rapid neutron capture, forging some of the heaviest elements in nature. This means that every atom in your body heavier than hydrogen was created in a star. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was forged in stellar cores billions of years ago and scattered into space when those stars died. We are quite literally made of star stuff, as Carl Sagan famously said. We are the cosmos contemplating itself, built from atoms that have been recycled through multiple generations of stars. The gas and dust expelled by dying stars don't just drift away into oblivion, they mix with the interstellar medium, enriching it with heavy elements. Eventually, this enriched material will be incorporated into new molecular clouds, which will collapse to form new stars and planets. The cycle continues: birth, life, death, rebirth. Stars form from the ashes of earlier stars, inheriting their chemical legacy, adding their own contributions when they die, passing it on to the next generation. This is happening throughout the galaxy. Old stars are dying as you read this. Planetary nebulae are expanding, their central white dwarfs slowly cooling. Somewhere, a massive star is in its final moments before core collapse. The shock wave is beginning. The supernova light has not yet reached us, but it's coming, traveling through space at 186,000 miles per second. When it arrives, astronomers will detect it, study it, learn from it. And in the nebulae created by these deaths, in the enriched clouds of gas and dust, new stars will form. The cycle that has shaped the galaxy for billions of years continues, driven by gravity and nuclear fusion, by the birth and death of stars, by the endless transformation of matter and energy that keeps the Milky Way alive, dynamic, ever-changing, even as its basic structure persists. The invisible scaffolding. There's something strange about the Milky Way, something that doesn't quite add up. It's a mystery that reveals itself through careful observation and mathematics, through the motion of stars and the behavior of galaxies. When astronomers measure how fast stars orbit the galactic center, they find something unexpected. According to Newtonian physics and our understanding of gravity, the orbital velocity of objects should decrease with distance from the center of mass. This is exactly what we see in the solar system. Planets farther from the Sun orbit more slowly. Mercury zips around the Sun every 88 days, while distant Neptune takes 165 years to complete one orbit. We'd expect the same pattern in galaxies. The visible matter, the stars we can see, is concentrated toward the center in the bulge and inner disk. So stars farther out should orbit more slowly, following what's called a Keplerian decline in velocity. The rotation curve, a graph of orbital velocity versus distance from the galactic center, should drop off at larger radii. But it doesn't. The rotation curve of the Milky Way, like those of most spiral galaxies, remains flat out to the edge of the visible disk and beyond. Stars far from the center are moving just as fast as stars closer in, orbiting at roughly 220 kilometers per second, regardless of their distance from the galactic center. This was first noticed by astronomer Vera Rubin and her colleagues in observations of other galaxies in the 1970s, confirming earlier work by Ken Freeman, who had observed this effect in NGC 300 and M33. The implication is inescapable. There isn't enough visible matter to account for the gravitational pull needed to keep these stars moving so fast. They should be moving more slowly, or if they're moving this fast, they should be flying off into intergalactic space, unbound from the galaxy. But they're not. Something is holding the galaxy together, providing the additional gravitational pull needed to explain the observed rotation. That something is dark matter. We call it dark because it doesn't emit, absorb, or reflect light. It doesn't interact electromagnetically, which means we can't see it with telescopes no matter what wavelength we use. We can only detect its presence through its gravitational effects. And those effects are substantial. When you add up all the visible matter in the Milky Way, all the stars, all the gas and dust we can observe, you get a total mass of roughly 200 billion solar masses, maybe up to 400 billion, depending on the estimate. That sounds like a lot, and it is. But the actual mass of the galaxy, determined from the motion of stars and gas and from the orbits of satellite galaxies, is far larger. Current estimates suggest the Milky Way has a total mass of somewhere around 1 trillion to 2 trillion solar masses, possibly more when you include the entire dark matter halo extending far beyond the visible galaxy. This means that about 90% of the galaxy's mass is dark matter. The stars, the planets, the gas clouds, the dust, everything we can see, all of it makes up only about 10% of the total mass. We're the minority constituent in our own galaxy, rare and unusual forms of matter living in a structure dominated by something we don't understand. The dark matter doesn't follow the same distribution as the visible matter, While stars are concentrated in a flat disk with a central bulge, dark matter forms a roughly spherical halo that envelops the entire galaxy. This halo extends far beyond the visible disk, possibly reaching out to 10 to 15 times the diameter of the disk itself. Some simulations suggest the dark matter halo could extend up to 2 million light-years from the galactic center, gradually thinning out until it becomes indistinguishable from the dark matter in surrounding intergalactic space. Within about 20 kiloparsecs, roughly 65,000 light-years from the galactic center, the dark matter mass is estimated to be about 1.4 trillion solar masses. The visible stars and gas within this same region contribute only a few 100 billion solar masses. The dark matter outweighs the visible matter by a factor of 5 or more. The density profile of this dark matter halo, how the density changes with distance from the center, is a subject of ongoing research. Different models give different predictions. The Navarro-Frenk-White NFW profile, derived from cosmological simulations, suggests a density that increases steeply toward the center, creating what's called a cusp. Other models, like the Burkert profile, predict a core with a relatively constant density in the inner regions, only declining at larger radii. Observations attempting to distinguish between these models have yielded mixed results. Some studies favor a cored profile, with a core radius of roughly 10 kiloparsecs and a central density much lower than NFW predictions would suggest. Other studies find evidence more consistent with a cuspy profile. The truth might lie somewhere in between, or the actual distribution might be more complex than these idealized models capture. What holds the dark matter halo together? Its own gravity. What keeps it from collapsing? The motion of the dark matter particles, whatever they are, provides pressure that balances gravity, just as the orbital motion of stars keeps them from falling into the galactic center. The halo is thought to have formed early in the universe's history, with the dark matter collapsing first under gravity, creating a gravitational well into which ordinary matter later fell, eventually forming stars and the visible structures we observe. But what is dark matter? That's the great unanswered question. We know what it's not. It's not ordinary matter, not protons, neutrons, and electrons in some hidden form. Such matter would interact with light and would have left observational signatures in the cosmic microwave background and in the abundances of light elements created in the Big Bang. The observations rule out ordinary matter as the primary component of dark matter. Leading candidates include various types of hypothetical particles. Weakly interacting massive particles, or WIMPs, are one popular possibility. Particles that have mass and interact through gravity and possibly the weak nuclear force, but not through electromagnetism. Axions, extremely light particles proposed to solve certain problems in particle physics, are another candidate. Some theories suggest primordial black holes formed in the early universe could account for some or all of the dark matter. Multiple experiments around the world are searching for dark matter particles, attempting direct detection by observing the rare interactions these particles might have with ordinary matter. So far, despite decades of searching, no direct detection has been confirmed. Dark matter remains elusive, detectable only through its gravitational effects, invisible to all our instruments except for the way it bends space-time and influences the motion of things we can see. And yet, Despite this ignorance, despite not knowing what it is, we can map its distribution, measure its mass, and understand its role in shaping the galaxy. Without dark matter, galaxies as we know them could not exist. The visible matter alone doesn't have enough gravity to hold together rotating disks of stars. Without the gravitational scaffolding provided by dark matter halos, galaxies would fly apart. The Milky Way would dissolve, its stars scattering into intergalactic space. Dark matter also played a crucial role in the formation of galaxies in the early universe. After the Big Bang, the universe was remarkably smooth and uniform, with only tiny density fluctuations. Ordinary matter interacting with radiation couldn't collapse quickly under gravity. Radiation pressure kept it dispersed. But dark matter, immune to radiation pressure, could collapse. Dark matter halos formed first, creating gravitational wells. Ordinary matter fell into these wells, pooling at the centers of dark matter halos, where it could cool, condense, and eventually form stars and galaxies. In this sense, we live not just in the Milky Way galaxy, but in the Milky Way dark matter halo. The visible galaxy is embedded in this larger, invisible structure. We're like inhabitants of a city built on bedrock we can't see, supported by foundations we only infer from the stability of the buildings above. The dark matter halo is our hidden foundation, the invisible architecture that makes our galactic home possible. It's humbling, isn't it, to realize that most of the galaxy's mass is something we don't understand, to know that we're made of the rare and unusual type of matter, the kind that clumps into stars and planets and people, while most of the cosmos is made of something else entirely, something that passes through us and all around us without us ever feeling it or seeing it. We detect its presence only through its gravity, through the way it shapes the motions of stars and the structure of the universe. But the fundamental nature of this dominant component of the galaxy remains one of the deepest mysteries in science. And that's okay. Not knowing is part of the human condition, part of what drives us to keep observing, keep measuring, keep asking questions. The mystery of dark matter is a reminder that for all we've learned, the universe still holds secrets, still has the capacity to surprise us and challenge our understanding. We live in a galaxy shaped by invisible forces, held together by matter we cannot see, and that makes our home all the more mysterious, all the more wondrous. Comparing homes. The Milky Way is our home, but it's not alone. The universe contains hundreds of billions of galaxies, maybe trillions, each one a vast collection of stars with its own structure, history, and character. How does our galactic home compare? The nearest large galaxy to the Milky Way is the Andromeda Galaxy, also known as M31 or NG C224. On a clear, dark night far from city lights, you can see it with your naked eye. A faint, fuzzy oval in the constellation Andromeda. It's the most distant object visible to the unaided eye, located about 2.5 million light-years away. For a long time, astronomers believed that Andromeda was significantly larger and more massive than the Milky Way, perhaps 2 or 3 times our galaxy's mass. This led to predictions that when the two galaxies eventually collide, an event expected in about 4 to 5 billion years, the Milky Way would be the smaller partner, likely absorbed into the larger Andromeda. But more recent measurements have revised this picture. In 2018, astronomers using a technique based on escape velocities, the speed needed for an object to break free from a galaxy's gravitational pull, determined that Andromeda's mass is much closer to the Milky Way's than previously thought. Both galaxies appear to have a total mass of roughly 800 billion solar masses, making them near twins in terms of overall mass. There are still differences, though. Andromeda appears to contain more stars, with estimates around 1 trillion compared to the Milky Way's 200 to 400 billion. However, Andromeda's stars tend to be older and less massive on average. The Milky Way has a higher rate of ongoing star formation, producing new stars more actively. Andromeda's visible disk is larger, stretching roughly 220,000 light-years across, compared to the Milky Way's 100,000 light-years. But when you include the dark matter halos, both galaxies become comparable again, with halos extending for hundreds of thousands or even millions of light-years. Both are barred spiral galaxies with similar structures: a central bulge, a bar, spiral arms, and a dark matter halo. Andromeda's bulge is larger, and its central supermassive black hole is more massive, weighing in at roughly 100 to 200 million solar masses, compared to our Sagittarius A star at about 4.1 million solar masses. Andromeda also seems to have had a more violent recent history, having merged with several smaller galaxies over the past few billion years. These mergers have left traces in Andromeda's structure, including streams of stars stripped from the smaller galaxies. Together, the Milky Way and Andromeda dominate the local group, a collection of more than 60 galaxies bound together by gravity. Most of these are dwarf galaxies, much smaller than either of the two giants. The third largest member is the Triangulum Galaxy M33, a smaller spiral with perhaps 40 billion stars. Then there are numerous dwarf galaxies. The large and small Magellanic Clouds, visible from the southern hemisphere as cloudy patches in the night sky, are satellite galaxies of the Milky Way. The Sagittarius Dwarf Elliptical Galaxy is even closer, currently in the process of being torn apart and absorbed by the Milky Way's gravity. On a larger scale, the local group is part of the Virgo supercluster, and that, in turn, is part of an even larger structure called the Laniakea supercluster, which spans about 520 million light-years and contains roughly 100,000 galaxies. We're connected through gravity to structures of increasing scale, part of the cosmic web of galaxies that fills the universe. How typical is the Milky Way? Pretty typical, it turns out. Spiral galaxies like ours make up roughly 60% of the large galaxies in the universe, with the rest being mostly elliptical galaxies, smooth, featureless ellipsoids, and irregular galaxies lacking any clear structure. Among spiral galaxies, the Milky Way is reasonably large, but not exceptional. There are bigger spiral galaxies and smaller ones. Our bar is neither especially prominent nor especially weak. Our spiral structure is well defined but not extraordinary. In many ways, this is reassuring. We're not special. We're not at the center of anything. We're not unique or chosen or particularly remarkable in galactic terms. We're just one spiral galaxy among hundreds of billions, orbiting one star among hundreds of billions of stars in that galaxy, hosting one planet among uncounted planets throughout the cosmos. And yet, to us, this unremarkable galaxy is everything. It's our context, our home, the structure that contains all of human history and experience. Every person who has ever lived has done so within the Milky Way. Every star we'll ever see with our own eyes belongs to this galaxy. If we someday spread beyond Earth, traveling to other stars, colonizing distant worlds, we'll still be contained within this same galactic structure, this spiral of stars we call home. The eventual collision with Andromeda will reshape both galaxies dramatically. The two will make several passes, their gravity distorting each other, stripping away streams of stars, creating long tidal tails of stars flung into intergalactic space. Eventually, they'll merge completely, forming a single giant elliptical galaxy that astronomers have nicknamed Milky Way. The new galaxy will be a different beast, no longer a spiral, lacking the ordered rotation and spiral arms. Instead, a roughly spherical swarm of stars orbiting in all directions. This sounds catastrophic, but for individual star systems, it will likely be uneventful. Space is so vast and stars are so small relative to the distances between them that actual stellar collisions will be extremely rare. Our Sun, if it still exists 4 billion years from now, will probably pass through the merger without coming particularly close to any other stars. The night sky will change dramatically though, filled with stars from both galaxies, bright and spectacular. But planetary systems will generally survive intact. For now though, and for the next few billion years, the Milky Way and Andromeda remain separate, two great spiral galaxies slowly drawing together across the void, while we, tiny and brief, watch from our vantage point inside one of them. The historical quest. Our understanding of the Milky Way is recent, hard-won, built up slowly over centuries of observation, debate, and gradually improving technology. For most of human history, we didn't know what the Milky Way was. We saw the band of light across the sky, but we couldn't grasp its true nature. Ancient cultures created myths to explain the celestial river. The Greeks said it was milk spilled from the breast of the goddess Hera. The Chinese called it the Silver River, a celestial counterpart to the Yellow River on Earth. Native American cultures had their own stories. Some saw it as a path for spirits, others as a seam in the sky where the fabric of the heavens was stitched together. These stories were beautiful, meaningful, deeply human attempts to make sense of what they saw. The first serious attempt to understand the Milky Way's structure came from William Herschel in 1785. Herschel, a German-born British astronomer, conducted careful star counts in different directions across the sky. He reasoned that if stars were distributed uniformly, then the number of stars he could see in any direction would tell him how far the Milky Way extended in that direction. His counts suggested a flattened structure, roughly disc-shaped, with the Sun near the center. He was right about the disk, but wrong about our position. We're not near the center at all, but the dust that obscures the inner galaxy made it appear as if we were. Throughout the 19th century, astronomers catalogued nebulae, fuzzy objects in the sky. Some, like the Orion Nebula, were clearly clouds of gas within our own stellar system, but others, like the Andromeda Nebula, were more mysterious. They showed spiral structure in photographs, earning them the name spiral nebulae. Were these gas clouds within the Milky Way, or were they separate stellar systems entirely, island universes comparable to our own? This question led to one of astronomy's most famous debates. In 1920, at the National Academy of Sciences in Washington, D.C., astronomers Harlow Shapley and Heber Curtis engaged in what became known as the Great Debate. Shapley argued that the spiral nebulae were relatively small, nearby objects within our own vast galaxy, which he believed encompassed the entire universe. Curtis countered that the spiral nebulae were distant, independent galaxies, making the universe far larger than anyone had imagined. The debate couldn't be settled with the data available at the time. But just a few years later, in 1923 and 1924, Edwin Hubble settled the question. Using what was then the world's largest telescope, the 100-inch Hooker telescope at Mount Wilson Observatory in California, Hubble identified Cepheid variable stars in the Andromeda Nebula. These stars have a known relationship between their period of variation and their intrinsic brightness, making them excellent distance indicators. Using this relationship, Hubble calculated that Andromeda was roughly 900,000 light-years away. The modern value is about 2.5 million light-years, but the crucial point remained. This was far too distant for Andromeda to be part of our own galaxy. It had to be a separate galaxy in its own right. The universe suddenly became vastly larger. The Milky Way was not the totality of existence, but just one galaxy among countless others scattered throughout space. But understanding our own galaxy's structure remained difficult. We're inside it, and interstellar dust blocks our view in visible light, especially toward the galactic center and along the galactic plane where dust is densest. For decades, astronomers struggled to map the spiral arms to determine our distance from the center to understand the overall structure. The breakthrough came with radio astronomy. In 1951, Dutch astronomer Jan Oort and his student C.A. Muller detected the 21-centimeter radio emission line of neutral hydrogen. This emission comes from a quantum mechanical transition in hydrogen atoms and can be detected by radio telescopes. Crucially, radio waves pass through dust unhindered, allowing astronomers to observe hydrogen clouds throughout the entire galaxy. By measuring the Doppler shift of this 21-centimeter emission, how much the wavelength is stretched or compressed due to motion, astronomers could determine how fast the hydrogen clouds were moving. Combined with models of galactic rotation, this allowed them to calculate distances to these clouds and start mapping the distribution of gas throughout the galaxy. For the first time, the spiral structure of the Milky Way became visible, traced out by clouds of hydrogen gas. The discovery of the galactic bar took even longer. Astronomers suspected its existence from peculiarities in stellar motions and gas distributions, but confirming it required infrared observations that could penetrate the dust and see the distribution of stars near the galactic center. The Spitzer Space Telescope, launched in 2003, provided the definitive evidence. Its infrared cameras revealed the bar structure clearly, showing a prominent, elongated distribution of stars at the galaxy's heart. More recently, the Gaia Space Telescope has revolutionized our understanding. Launched by the European Space Agency in 2013, Gaia's mission is to create the most precise three-dimensional map of stars in the Milky Way ever made. It measures the positions, distances, and motions of over 1 billion stars with unprecedented accuracy. The data from Gaia has revealed subtle patterns in stellar motions that betray the gravitational influence of spiral arms and the bar, confirming and refining our models of galactic structure. The BSL survey, Bar and Spiral Structure Legacy Survey, has used very long baseline interferometry to measure the parallax and proper motion of masers, natural radio sources associated with star-forming regions. These measurements are accurate to within a few percent, providing some of the best distance measurements to objects throughout the galaxy and revealing the positions of spiral arms with remarkable precision. Each technological advance has brought new insights. Optical telescopes revealed stars, radio telescopes revealed hydrogen gas, infrared telescopes saw through the dust, X-ray telescopes detected hot gas and exotic objects like neutron stars. Gamma-ray observatories revealed high-energy processes and allowed estimates of star formation rates based on radioactive isotopes. And space telescopes, above Earth's blurring atmosphere, provided the clarity needed to measure positions and motions of individual stars across vast distances. Yet even with all these tools, mysteries remain. The exact number of spiral arms is still debated. Do we have 2 major arms, 4 main arms, or some more complex structure with multiple arm segments and spurs? The shape and extent of the dark matter halo remain uncertain. The detailed history of the galaxy, how it formed, what mergers it has experienced, how its structure has evolved over billions of years, is still being pieced together from observations and simulations. This is the nature of science. It's cumulative, iterative, constantly refining its understanding as new data becomes available. What we know about the Milky Way today is vastly more detailed and accurate than what we knew a century ago, and a century from now, our understanding will be even deeper. But it's built on the work of countless astronomers, physicists, mathematicians, engineers, and technicians, each contributing their piece to the growing portrait of our galactic home. We can be proud of what we've learned and humble about what remains unknown. We've gone from seeing a cloudy band of light and weaving myths to understanding that we live in a barred spiral galaxy 100,000 light-years across, containing hundreds of billions of stars embedded in a dark matter halo 10 times larger, part of a local group of galaxies in a universe filled with hundreds of billions of such galaxies stretching to the limits of observability. That's an extraordinary journey of discovery, and it's not finished yet. Living inside wonder. There's something uniquely beautiful about living inside the thing you're trying to understand. We can never step outside and see the Milky Way from a distance, never get that perfect, complete view that would reveal every detail of its structure. We're embedded within it, surrounded by it, constrained to observe it from our single vantage point within the galactic disk. And yet, from this imperfect position, we've learned so much. We've mapped the spiral arms we can never see as spirals. We've traced the bar we view almost end on. We've measured the dark matter halo we can never directly observe. We've determined our distance from a galactic center hidden behind thousands of light-years of dust. We've done all this through indirect methods, through clever observations, through mathematics and modeling, through the patient accumulation of data and the gradual refinement of our understanding. When you look up at the night sky and see the Milky Way band stretching overhead, you're seeing your own galaxy from the inside. Most of what you see lies in the galactic plane, the thin disk where most stars reside. The brightest region, in the constellation Sagittarius, marks the direction toward the galactic center. Though you can't see the center itself, it's hidden behind dust clouds that block visible light. Every star you can see with your naked eye belongs to your local neighborhood. They're almost all within a few thousand light years, and most are much closer. The stars that form Orion, the Big Dipper, Cassiopeia. These are nearby stars, local features of the Orion Arm and adjacent regions. They're your galactic neighbors, relatively speaking, even though the nearest of them is light years away. Beyond what you can see directly lies vastly more. The galaxy extends 50,000 light-years beyond your position, filled with billions of stars your eyes will never resolve. The galactic center, 27,000 light-years distant, hosts a supermassive black hole about 4.3 million times the mass of the Sun. Around this black hole, stars orbit at incredible speeds, whipping around in orbits that take years or decades rather than the 225 million years our Sun requires. The central bulge contains some of the galaxy's oldest stars. Metal-poor population 2 stars formed when the galaxy was young, when the universe itself was only a few billion years old. These ancient stars witnessed the galaxy's youth, saw the first generations of structure forming, the settling of matter into the disk, the emergence of spiral arms. Some globular clusters orbiting the galaxy are nearly as old as the universe itself. 13 billion years or more, containing stars that formed when the cosmos was barely 500 million years old. The disk where we live is younger, more metal-rich, actively forming stars. It's organized into a thin disk where most stars and gas reside, and a thicker disk of somewhat older stars with more random orbits. The thin disk is only about 1,000 light-years thick, incredibly flat relative to its diameter. It's like a sheet of paper scaled up to cosmic dimensions. And enveloping all of this is the stellar halo, a roughly spherical distribution of old stars and globular clusters extending far beyond the disk. This halo is sparse, the stars are few and far between, but it traces out a much larger structure. And beyond even that lies the dark matter halo, invisible but massive, extending perhaps 1 million light-years or more from the galactic center, gradually fading into the dark matter that fills intergalactic space. The galaxy rotates, but not as a solid body. Different parts rotate at different speeds, following what's called differential rotation. This is why density waves can exist, why spiral arms can persist even as stars pass through them. It's also why, over time, the galaxy mixes and evolves, with stars gradually migrating inward or outward from their birthplaces, with gas being funneled around by the bar and spiral arms, with structure emerging from the interplay of gravity, rotation, and stellar feedback. Our Sun has been orbiting the galactic center for 4.6 billion years, completing about 20 full circuits. In all that time, the galaxy has changed. New stars have been born, old stars have died, supernova explosions have scattered heavy elements, molecular clouds have collapsed and dispersed. The specific arrangement of stars has shifted, and yet the basic structure has remained, the disk, the bulge, the spiral pattern persisting even as the details change. In another 200 to 25 million years, the Sun will return to roughly this same position in its orbit, but the galaxy it inhabits will be slightly different. Some of the stars we see now will have moved away. New stars will have formed. The spiral arms will have shifted. Life on Earth, if it still exists, will have evolved in ways we can't predict. But the galaxy will still be here, still rotating, still breathing with star birth and death, still held together by the dark matter that forms its invisible skeleton. Human civilization is unimaginably brief by galactic standards. All of recorded history, from the first written records to the present day, spans perhaps 5,000 years. In that time, the solar system has moved about 1/50,000th of the way around its current galactic orbit. We are a flicker, a momentary spark in the galaxy's long story. Individual human lives are even briefer. In a human lifetime of 80 years, the Sun moves only about 14 billion kilometers in its galactic orbit, a distance that sounds large but is only about 90 times the distance from the Sun to the Earth. On galactic scales, it's nothing. We barely move at all. And yet, in this brief moment, in this tiny slice of the galactic story, we've become aware. We've developed consciousness, intelligence, curiosity. We've looked up at the stars and asked what they are. We've built telescopes and spacecraft, gathered data, developed theories, tested them against observations. We've figured out where we are, what surrounds us, how the galaxy is structured, how it formed, how it will evolve. We're made of atoms, forged in stars, scattered by supernova explosions, gathered by gravity into new clouds that collapsed to form our sun and planets. The carbon in our cells, the oxygen we breathe, the calcium in our bones, all created in stellar cores and stellar explosions, recycled through the interstellar medium, incorporated into the molecular cloud that became our solar system. We are, quite literally, the galaxy's material reorganized into living, thinking forms. We are the galaxy contemplating itself, the cosmos become conscious. There's something profound in that. We're part of the galaxy, not just in it. We're made of its material, shaped by its processes, products of its long history of stellar birth and death and chemical enrichment. The iron in our blood was forged in a massive star that exploded as a supernova billions of years ago. The atoms of our bodies have been recycled through perhaps dozens of stars over the galaxy's 13.6 billion year history. We carry within us the legacy of cosmic evolution. And in recognizing this, in understanding our connection to the larger whole, perhaps we can find some measure of peace. We're tiny and brief, yes, but we're part of something vast and ancient. The galaxy was here, long before us, and will continue long after we're gone. Stars will keep being born and dying. The spiral arms will keep rotating. The great slow dance of matter and energy will continue. Our individual lives matter and don't matter simultaneously. We're insignificant in cosmic terms, brief sparks of consciousness in an enormous, largely indifferent universe. And yet, to ourselves and to each other, we matter immensely. Our experiences are real, our joys and sorrows significant, our discoveries meaningful. We're both vanishingly small and cosmically important, small in scale, but profound in our capacity for awareness, understanding, wonder. This is what it means to live inside wonder, to be embedded in something so much larger than ourselves that we can barely comprehend it, and yet to understand enough to know where we are, to grasp the basic architecture of our galactic home, to recognize our connection to the deep history of stellar evolution and cosmic structure formation. We are citizens of the Milky Way, residents of the Orion Arm, inhabitants of the galactic suburbs, products of billions of years of cosmic evolution. We're made of star stuff, contemplating star stuff, brief patterns of organized matter experiencing the universe from the inside. And for this moment, this brief window of time, we're here, aware, able to look up and understand, able to see the Milky Way band stretching across the darkness, and know, truly know, what we're seeing. The quiet home. So here we are, at the end of our journey through understanding, though in another sense we've never left where we started. We began with the experience of looking up at the Milky Way band on a clear, dark night, that river of faint light stretching across the sky. And now, having explored the galaxy's structure, its spiral arms and central bar, its star-forming nurseries and supernova remnants, its dark matter halo and its place among other galaxies, we return to that same image, but transformed by understanding. When you see the Milky Way now, you know what you're looking at. That band of light is your own galaxy seen edge-on from within, the combined glow of billions of stars too distant to distinguish individually. The dark patches aren't gaps in the stars, but dust clouds, stellar nurseries where new stars are being born even now. The brightest region toward Sagittarius marks the direction to the galactic center, where a supermassive black hole lurks, surrounded by ancient stars in the dense central bulge. You know that you're embedded in a disk of stars 100,000 light-years across, but only 1,000 light-years thick, a flattened structure shaped by rotation and gravity. You know that this disk is organized into spiral arms, great sweeping structures that emerge from a central bar and wind outward through space. You know that your sun, your planet, everything you've ever known or experienced, resides in the Orion Arm, a relatively minor structure between the major Perseus and Sagittarius arms, about 27,000 light-years from the galactic center. You know that the visible stars, as numerous as they are, represent only a small fraction of the galaxy's mass. Most of it is dark matter, invisible but essential, forming a vast spherical halo that envelops the visible galaxy and holds it together through gravity. You know that stars are constantly being born in molecular clouds and dying in planetary nebulae and supernovae, their deaths enriching the interstellar medium with heavy elements that will be incorporated into future generations of stars and planets. You know that the galaxy is ancient, 13.6 billion years old, nearly as old as the universe itself, and that it has evolved slowly over that vast span of time, accreting material, forming stars, developing its spiral structure through billions of years of gradual evolution. You know that it will continue to evolve, that in a few billion years it will collide with Andromeda and merge into a new, different kind of galaxy, though by then our sun will likely be nearing the end of its life, swelling into a red giant that will consume the inner planets. All of this, you know, or at least have some understanding of, even though you can never see the galaxy from outside, can never get that perfect view that would reveal its full structure at a glance. You're like someone who has learned the layout of a vast city by walking its streets, by studying maps drawn by others, by carefully observing patterns and inferring the larger structure. You don't have a bird's-eye view, but you understand the shape of your home nonetheless. There's something beautiful in this achievement. Humanity has mapped the Milky Way from the inside, pieced together its structure from fragments of observation, built up a coherent picture of the galactic architecture despite the limitations of our embedded position. We've done this through ingenuity, through the patient accumulation of data, through mathematical modeling and physical reasoning, through the steady improvement of our instruments and techniques. It's a triumph of curiosity and persistence, of the human drive to understand. And in understanding, we've found our place. We're not at the center. We never were, despite what earlier astronomers believed. We're out in the galactic suburbs, in a minor spiral arm, orbiting a fairly ordinary star. We're recent arrivals in galactic terms, products of the last few billion years of stellar evolution and planet formation. We're made of recycled star material, temporary organizations of atoms that will eventually be returned to the interstellar medium when our Sun dies and the Earth along with it. We're insignificant in one sense, tiny specks in an enormous structure, brief moments in a history that spans billions of years. And yet we're also extraordinary. We're conscious. We're aware. We can contemplate the galaxy and our place in it. We can look up at the stars and understand what we're seeing. We can trace the spiral arms, infer the dark matter halo, measure our distance from the galactic center, predict the eventual collision with Andromeda. We can do all of this despite being embedded in the very structure we're studying, despite being made of the same material we're observing, despite existing for only the briefest flicker of galactic time. The Milky Way is always above you, whether you can see it or not, whether you think about it or not. It's turning slowly, taking about 225 million years to complete one rotation, carrying you along as the Sun orbits the galactic center at roughly 230 kilometers per second. Stars are being born in its molecular clouds as you read this. Somewhere, a massive star is approaching the end of its life, about to explode as a supernova. White dwarfs are slowly cooling in the darkness. Neutron stars are spinning hundreds of times per second. The supermassive black hole at the center is accreting material, occasionally flaring in X-rays as matter falls into it. All of this is happening, has always been happening, will continue to happen for billions of years to come. The galaxy doesn't care about you. It doesn't notice your existence. It's not aware of itself, of its structure, of its history. It simply is. A vast collection of matter and energy organized by gravity and rotation, evolving according to physical law. But you care about it. You notice it. You've become aware of it, learned about it, developed some understanding of what it is and how it works. In you, the galaxy has become self-aware, at least in a small way, at least for a brief moment. And that's worth something. That's meaningful, even if the meaning exists only in your own mind, only in the collective understanding of humanity. So tonight, if you can, go outside to a dark place away from city lights. Look up. Find the Milky Way band stretching across the sky. See it not just as a pretty band of light, but as your galactic home, the structure that contains everything you know and everything humanity has ever experienced. See the dark dust lanes as stellar nurseries. Know that the bright regions are concentrations of distant stars. Understand that you're seeing the galaxy from within, that you're part of what you're observing. Feel the wonder of it, the deep, quiet amazement at the scale and the age and the beauty of this vast structure we call home. Feel your smallness, yes, but also your connection. You're made of this galaxy's material, shaped by its processes, part of its ongoing story, even if only briefly, even if only in the tiniest way. And maybe in that moment of recognition, you'll find some measure of peace. Peace in knowing where you are. Peace in understanding that you're part of something immense and ancient. Peace in the realization that the galaxy will continue long after you're gone, that your atoms will be returned to the interstellar medium and perhaps someday incorporated into new stars, new worlds, maybe even new forms of life. The Milky Way, our silent galactic home, always there, always turning, always beautiful in its vast, slow dance through space, and we, briefly, wonderfully, get to be part of it. If you've enjoyed this cosmic exploration, and if these quiet journeys through space and time help you drift into restful understanding, consider subscribing to the channel. There are more wonders to explore, more questions to contemplate, more peaceful wanderings through the cosmos waiting for you. Until next time, rest well under your galactic home.